Hello, everybody, ladies, gentlemen, and non-binaries, and a special nerd day to everybody. May the 4th be with you. I have been waiting to make that joke for a good 2 months now. I'm not going to lie. I'm Amelia Thompson, your host of the Worth Electronic Webinars, and joining me today is Stefan Bechel. I hope I didn't mispronounce that. I am so sorry if I did, Stefan. Stefan is a field application engineer with Worth Electronic in Germany, and today he will be presenting temperature rise and derating of connectors, of course, powered by our exclusive sponsor, Digi-Key Electronics. In just a few reminders before we get going today, because you registered for today's event, you will automatically receive the video on demand and the presentation slides following the event within 24 to 48 hours. Just be looking for a follow-up email from here for you at we-online.com. And if you have any questions during today's event, simply ask them in the questions box. Stefan will answer them at the end. Now, if you come in late or you think of a question a little bit later, don't worry, you can always ask them in a follow-up email. Again, that's here for you at we-online.com. Don't forget to register for our next webinar coming up this Thursday, actually, LAN on Command. Learn about the importance of LAN transformers in Ethernet devices. And now I'm going to pass it over to Stefan as he presents temperature rise and derating of connectors.
Thank you very much, Amelia. So good morning, America. Good morning, Canada. Hello to everybody on this planet. So I'm very excited to have you here. Thank you so much for registering. And I hope you will enjoy the webinar we have today together. My name is Stefan. I'm in the company Worth Electronics since 2011, and I work as a field application engineer for the electromechanical components. What does this mean, electromechanical components? I take care about connectors, about switches, and some assembly products. Normally, I'm responsible for the customers here in the south of Germany and also doing international integration trainings in our company and sometimes international webinars like today. Today, we will not talk about assembly, we will not talk about switches, we will talk about connectors. And I have the topic for you, connector temperature rise and derating. Why do we talk about temperature rise and derating regarding connectors? Well, let's say it like this, during the last years in the field, I saw many applications which have to deal with a lot of power or with a lot of current. So sometimes the designer was not aware of the derating curves of a connector or to respect the derating of a connector. So the application sometimes failed and got too hot. And to avoid things like that, we've got this small presentation today for you. Please enjoy the webinar. We get right started now. So what are we talking about today? Yes, we are a manufacturer of connectors, as you know. So how can we find as a manufacturer the right working current for our connectors? I will show you that in a few slides. After that, we will talk about consequences of a too high temperature inside of a connector. Therefore, we have to look at the temperature rise rules. And when we have too much heat in our system, we have to find an idea how the heat can be dissipated. And there are different possibilities to dissipate the heat, and one very good is to dissipate it in the cable we have on our connector. So that's the point where we are talking about heat in a cable. Then I have also some tricks for you, or maybe answer some questions which popped up with your application and your current. Then we have a look at the derating curves. And at the end, I will show you some examples where we have 3 times high currents put on connectors and see what's happening. In these cases, we call it connector horror show. And at the end, a few things you have to remind when you're dealing with high currents and connectors. So the first picture you can see here is not so nice, but this was reality. This is a real application from a customer here in Germany, not a small one, it was a big customer. And this is a wire-to-wire connection here with a terminal block with a 5.08 millimeter pitch, 2-pole with a cable around AWG12. And this connector was powered with 20 amps, but the connector was stored in a closed box. So the heat had no possibility to dissipate, and this was the reason why this connector really burned. And at the end, we had no connection anymore, so this application was destroyed by using the wrong connector. To avoid this, I will bring you this presentation today. So how can we find the right working current for a connector? Let's have a look on a typical power connector. You know them all. It's a typical terminal block as we have it in our catalog. This one is also a 5.08 pitch connector. It's a 3-pole. And when we look at the data sheet says it has an operating temperature from -40 degrees up to 105 degrees Celsius. So sorry for being not in Fahrenheit here. It's a European presentation. We have it in Celsius. So this is the range where the operating temperature of the connector works. But does this mean I can add 20 amps on this connector at 105 degrees? No, we cannot do that. We have to respect the derating. And we will see how we can fix our current for our connector in the next slides. So first of all, when we have a look at the electricity and the temperature rise, we have some simple rules. We have a resistor. A connector is also a resistor. Remember, it has a resistance inside. So this resistor has an ambient temperature or room temperature called T. Now, when I put some current on this connector, the resistor or the connector gets a little bit warmer, means we have the temperature, the room temperature, the ambient temperature, plus the delta from the heat, which comes from the current we put into the connector. So how can we design our connector regarding the currents? We have to do a so-called temperature rise test. And there is also a standard for it. We use the standard EIA 364-7T and also the UL 1059 standard. And this standard says if you want to do a temperature rise test with a terminal block, you have to use a 3-pole terminal block. You have to put the current in series because then the current is everywhere the same regarding the connector. And then you do the test and reach the stable temperature. You have to do 3 measurements. Each 5 minutes, the temperature is not allowed to swap more than 1 degree Celsius. And then we have to take care about the hottest point. There are some regulations, one from UL, the Underwriter Laboratories in the USA, you know them all, I think, and one of VDE, this is more or less a German or European specification. And when we look at the UL 1059, we have to respect the UL specification, especially for applications that run in the American or Canadian market. And UL says the delta T of a power connector must be under 30 Kelvin. So we have to test this. So what do we need? We need a chamber to avoid air movement, as you can see it here right on the picture. And then we need some thermocouples. What is a thermocouple? It's a simple thing. Those are 2 wires made out of different materials. And if you change the temperature on those wires, they give a little voltage on the system. And this little voltage can be detected, and it says you the exact temperature of the point where you store the thermocouples. Those thermocouples have to be stored at the hottest point of the connector. And as you can imagine, the hottest point is in the middle of the connector. When we have the 3-pole, we have to store the thermocouples at pole 2. This is what you can see here, the hottest point. There the thermocouples are installed. And then we have to do an electric assembly regarding the UL standard. And this standard says if you want to check a terminal block, you have to use a 1 meter long wire with an AWG12, and the AWG12 is suitable for 20 amps. So we try out to specify our connector with 20 amps. So you can see the assembly, and now we put on the 20 amps on our assembled connector. And this is what happened. We had made a picture with a thermal camera, and we measured the hottest point. It's the point SP1, as you can see here in the middle of our connector. And remember, the delta T must be under 30 Kelvin. So let's check what happened. So we had an ambient and room temperature of 21.7 degrees Celsius. And then we put 20 amps on this connector, and the delta is 24.8 Kelvin. That means the end temperature was 46.5 Celsius minus the ambient temperature gives us the delta, and the delta in this case is 24.8 K. That means it's absolutely okay for our connector, because we said it must be under 30 Kelvin. Okay, theoretically, we can go up to 22 amps like that, but we don't do because the AWG12 cable is suitable for 20 amps. So we specify this connector with 20 amps, and we are on the safe side then. So now you saw how we specify our working current for our power connectors. And now we have to check what happens if we have too much heat on our connector. Let's say the consequences of too high temperatures. First of all, we have to look at the metal parts of our connector, and there is the possibility to increase corrosion speed. When we increase the corrosion speed, we naturally also increase the contact resistance. But what happens if we increase the contact resistance? Okay, the product gets warmer again, and when the product gets warm and warm and warm again, we increase already the corrosion speed again. So this is really a vicious circle. We have to take care about that. Let's have a look at our copper alloy, because most of the power connectors are made of any copper alloy, for example, brass. And when we look at the material temperature curve regarding the electrical resistance, we see that we have additional 20% resistance each 50 degrees Celsius. So this is really a vicious circle. We have to take care about that. But not only on the metal parts in our connector. You know, a connector does not have only metal parts. There are also plastic parts in it, which can melt, as we saw on the picture before, or which can burn. So we have also to have a look on the plastic material. What happens with the plastic material if it gets too hot? It ages faster, so the color will change, and someday it will also break because of embrittlement. Therefore, we have to respect the RTI, the relative thermal index of our plastic material. So let's have a look at the table here. The RTI says 125 degrees is okay for polyamide. So standard terminal block is made out of polyamide. So, and that is the reason why we say the maximum operating temperature for our terminal block is 105 degrees. There's a margin of 20% inside, so that we do not reach the relative thermal index of this material. This relative thermal index, where does it come from? It's defined in the standard UL 746C. It shows the temperature from which the speed of aging of the plastic is accelerated. So if we want to have a proper application, we always have to stay under this RTI, under this relative thermal index. And we do with our connectors, as you can see a few slides later too. There's another thing we have to respect. What about the relaxation of our metal parts in the connector? You know, most of the connectors have on one side a pin, on the other side a fork like this one, and this fork has the function of a spring. It just grabs our connector and gives us a defined force here on our pin. But over the years, we also have a kind of metal relaxation. So that means if the connector gets older and older and the application is in the field for around, let's say, 10 years, then the metal gets relaxed a little bit, and also the resistance increases at this point. And when we increase the temperature in our application, that means the application is always very warm, then it will go faster, as you can see here on the table. So when we look at the red line is at ambient temperature from 20 degrees Celsius. So over 100,000 hours, that means around 10 or 11 years, almost nothing happens. But if we have a temperature in our application around 150 degrees, so at the end of the connector range, for example, Then it's a little bit difficult. So you can see the blue curve. Then it started earlier to relax. The metal materials relax a lot earlier. So we have to take care about also the metal relaxation. So what do we have to respect too? The most important thing, our temperature rise rule. And there is also a special thing when we look at the power and when we have a look at Joule's law. Joule's law says the power in watts is the resistance multiplied by the current in square. So we have to respect the current in square. And what about the temperature rise? The temperature rise, delta T, is the constant, the material constant of our connector multiplied with the resistance multiplied with the square of the current. So this is really crazy. Temperature rise is proportional to the square of the current. That means if I double my current, I have 4 times more warming. And this is really dangerous when we have a look at our applications. So there is the theoretical calculation. You see the formula on the right side. And I give you an example. When we put an I1 of 15 amps on our connector or on our resistor, which is the same in this case, it gives us a delta T of 15 Kelvin. Say the temperature rise was 15 Kelvin at 15 amps. Do we put on the connector 30 amps instead of 15? We have to calculate it with the formula you see on the right side. Then the delta T2 is 30 square divided by 15 square multiplied by 15. And this gives us a temperature rise of 60 Kelvin, 4 times higher than before. That means double current, 4 times higher temperature rising. Please take care of that. So is this really true? We also did a temperature rise test with our connector, as I showed you before on the slides before. And we did now a calculation and we have to compare those two curves. And when we compare the calculation curve and the measurement curve, it's exactly the same. So it's really the case, if you double the current, you have 4 times warming on the connector. What do we have to remind in this case? Each resistance releases heat under current. The working current is designed regarding UL with a delta T of 30 Kelvin maximum, and regarding the VDE standard here in Europe, it's a delta T maximum of 45 Kelvin. And we have to respect the maximum working temperature of the plastic material regarding the relative thermal index. The most important thing, temperature rise is proportional to the square of the current. So now we have double current and we have 4 times more warming, and now we have to take care about how can we dissipate the heat again. So we come to just to the next point, how can the heat be dissipated? Therefore, we have a look to a small fire. Everything knows how a fire works, and there are different possibilities to dissipate the heat from a fire. The first one is convection. That means the dissipation through the air around the heat source. Natural movement of the air. It will go up when it gets hot and it will come down when it gets cold. And then it will be heated and then come up again. So if you stop this movement, like putting it in a closed box, the convection does not work in a proper way. But we do not have only the possibility with convection to transport the heat away, to dissipate the heat. We also have the possibility with conduction. So let's say if you put a metal bar into a fire and you touch it on the other side, you know what conduction means. So it gets very hot at this side. It's the dissipation through a material that is touching the heat source directly. In that case, in our case, it's cable and PCB. In that case, it's a metal bar. We will see the importance of the wire lengths in the presentation a few slides later. But this is not all. There is still one left. Still one possibility left to dissipate the heat. It is radiation. It's a little bit more complicated than the other two. Radiation is the heat dissipation through light emission. Light frequency, let's say light color, depends on the temperature. This is the principle of a thermal camera. And this is also the way how the sun heats the earth through billions of kilometers of frozen vacuum. So the sun is far away, we have a lot of frozen vacuum in between us, and we get still warm because of the sun, because of radiation. But we do not have a fire in our application, hopefully not. We have a connector in our application and a cable and a PCB. When we look at those possibilities to dissipate the heat, we look first at the point conduction, and the heat can be dissipated over the cable and also a little bit over the PCB. So the dissipation over the cable is much more important regarding a connector system. So we take care about the cable now and not about the PCB. We also do tests how to design a perfect PCB, but we are not ready with these tests. That has to do something with the COVID situation here in Europe. So we are not able to go to our labs and do our tests in a normal way in these days. So I hope this will change soon, and we will be ready with those measurements regarding the PCB about July. And then we will launch also a design guide for terminal blocks online. You can find it on our website then in the middle of the year, let's say around July, August, and there you can read also something about conduction regarding over the copper tracks on our PCB. Okay, but we have also the convection on our applications. That means the warm air goes also up, and when we have our application in a closed box, we have to take care about that, because then the convection doesn't work anymore in a proper way. And we have to deal also with the radiation. Therefore, we have to look a little bit closer to the different materials we have for our connectors. Let's go over those three things point for point. We will start with the formula. The energy, the thermal energy in joule is W, is power multiplied by the time in second. So that means the longer you put the current on the PCB, the warmer gets the application. So first have a look on the conduction. Therefore, we have the Fourier's law. It's quite easy. It says the delta T is the length divided by lambda multiplied by the section of the material we have inside our wire, for example, or with our cable, multiplied by the power. So that means when we have a look at the thermal conductivity lambda, you can see the lambda here in the formula, and this lambda says the thermal conductivity. And when we have a look at it, it says copper has the best thermal conductivity of our materials in the connector. So this is also a reason why we use copper wires. Those copper wires are perfect to dissipate the heat from our connector, just to grab it from the connector and put it in the air, for example. Also, aluminium has a good thermal conductivity. When you remember your coolers you have on the chip, for example, most of them are made of aluminium. Some are made also of copper, but copper and aluminium are good materials to transport the heat away, to dissipate the heat. Also, brass is very good, but the other things like glass, water, plastic materials, and the worst one is air. So to use the conduction to bring the heat away, we have to use our metal materials in our connector. That means best conduction material is copper. The bigger the copper wire is, the best it is. And plastic is not so good for the conduction dissipation, just good for radiation dissipation, as we will see a few slides later. But before radiation, we will have a look on convection. Convection, you remember, was the airflow over the material. And therefore, there's also a formula. It's called the Newton's law. And the thermal flow is the convection coefficient multiplied by the square and the section, sorry, and the temperature of the material. So that means if we increase the surface in contact with the air, it increases thermal dissipation. That means the more surface we have, the more possibility we have to have a thermal dissipation through convection. When we look at the point radiation, there is also a formula behind. You can see it now on the right side. We can look at the thermal flow. There we have a so-called surface emission factor and the Boltzmann constant. We can calculate the radiation. And if we do a calculation like this, the effect of the radiation is more efficient if the higher the surface temperature is, the lower the temperature outside is, the higher the emission factor is. It's higher for plastics than for metal. It's a little bit special here. And the bigger the surface is in contact with outside. So I have also a simple test for you how you can test radiation. Just take two pens, a white one and a black one, and store them into the sun. And then if you come back half an hour later, you will see that the black pen is much more warmer than the white pen, and this has to do with the radiation. So the best material we already said is plastic materials, and dark plastic materials is better than white plastic materials. Dark matte surface is the best we can have for thermal dissipation through radiation. Therefore, for example, we have a FR4 material with a dark matte surface. It has a good thing, but also aluminum anodized is not bad. But then if you have aluminum polished, it's not so good to give us radiation. So that means plastic radiation dissipation is highly better than metal. Metal unpolished is highly better than polished one. We'll come back to this point when we have a look at the polarity of our connectors. So we do the tests, the temperature rise tests, as you saw before, with a 3-pole connector. But what about a 12-pole connector? There we have more space. There we have more plastic material, more possibility for radiation. But we come to this point later. First of all, what do we have to remind regarding heat dissipation? An electrical system must have thermal exchanges. Undercurrent temperature should be stabilized after 10-15 minutes. Regarding radiation, plastic is better than metal. Rough metal surface is better than polished. And regarding the convection, we have to increase our surface in contact with air. Then the convection is better than before. Regarding conduction, copper is the best material for conduction dissipation, so that's why we use our cables made out of copper. And if we increase the section, we optimize the exchange. And now we will have a little closer look on the cable, because the cable is really important when we have an application running with a terminal block and it gets hot. You can do a lot of things using the right cable. Now we come at the point heating the cable, and there are also some tables behind. What kind of wire for what kind of current? There are some certification organizations which give us some rules for that. Regarding the UL again, we have the UL 486. And the UL 486 says, for example, if we have a wire size AWG12, we can add maximum of 20 amps current on this cable. And the wire size in square millimeter is 3.3 in this case. And regarding the IEC, this is suitable for Europe. It's the same as VDE. It says it's not so conservative as the UL one. So when we'll have here a cable around 3.3, yes, we are in between here. We can add between 24 and 32 amps on the cable. But there is another VDE table existing, but there you have to take care. This has nothing to do with electronics. So the VDE table on the right side is just designed for wires which have no insulation, which are just going through the air. For example, the wire which go from house to house for the mains or for the telephones and so on. There you can apply a lot more current because there's no insulation on it. But this table is not useful for electronic products. When we deal with electronic products, we have to look at those two tables. This one, if we want to sell the product in the US market or the Canadian market, and if we want to sell it in Europe, we have to respect the IEC 16998-1. So how can we calculate the resistance in the wire? This one is quite easy. We have the length of the wire and we have the section of the wire. And the formula behind this, the resistance is the material resistivity multiplied by the length of the wire divided by the section of the wire. So we can calculate the wire resistance. But what is the temperature rise with wires? So therefore, we did a test again with a delta T of 50 centimeter wires. Therefore, we removed also the insulation and we stick 2 thermocouples directly on the copper conductor. We used a AWG12 cable with a 20 amps as before with a connector, and you see the measures here. It's between 23 degrees Celsius, and 34.7 degrees Celsius. So that means we have a delta T lower than the delta T of the connector in our cable. If we have an AWG20, we have a delta T at 5 Kelvin on the cable. If we use AWG12, we have, with our example here with the 20 amps, we have a delta T of 11 Kelvin. So the cable warms around 11 Kelvin, but the connector can warm around 30 Kelvin. That means the cable pulls out the heat out of the connector. Delta T increases proportionally to the wire size, and the wire heats less than the connector. It has always be below the connector. The connector is allowed to heat to 30 Kelvin. So, okay, we talked now about the wire size, about the AWGs, but what is the right length to dissipate the heat? We didn't know that before. We had really to make some tests about that, and we did it like this. We had also the terminal plug with the 3-pole you saw before. This time it's another pitch, it's 7.62 millimeters with a different wire length, and we have 2 thermocouples and 2 TBL clamps inside. And we measured the temperature on the cable. There you can see the connector heats 26.3 Kelvin. It's all right, it's below 30. And the cable, which is close to the connector, has a temperature rise of 19.4 Kelvin. And this goes for a long time, and then sometimes it drops down to 17.8 Kelvin. So what about if we use a really quite short cable? We tried this with this one, also AWG12, also 20 amps, 2.5 centimeters. And as you can see in the thermal picture here, the cable gets very hot, and the connector also gets very hot. This means the connector goes above the 30 Kelvin, and the cable is not it's not possible for the cable to pull out the heat of the connector in this case. So we had to check this, which is the right length. So we had to measure this, and we found out that the right length to dissipate the heat out of a connector is between 10 and 15 centimeters. If the cable is longer, nothing more happens. If the cable is shorter, the connector gets too warm. So that means optimized length for heat dissipation, 10 to 15 centimeters. And it's also a question of money, because if you have a long cable and it doesn't make sense to use it, you just have to pay it. So 10 to 15 centimeters is the optimum here. Less will increase internal connector temperature. We cannot do this with less cable, because then we are above the usual or the allowed 30 Kelvin, and more is useless for thermal dissipation. Yeah, the right size of the wire. Therefore, we also checked some things. We tried out an AWG16, we tried out an AWG14 and an AWG12, and the internal connector temperature went down. The thicker the cable, the lower the AWG. So that means, but also you have to pay more for it. Increasing the wire sizes decreases our delta T, but the cost decision is yours in this case. You always have to take care in between the costs and the temperature. So what do we have to remind? Copper wires heat less than the connectors itself. Wires are used to dissipate heat out of the connector, and the optimized length is 10 to 15 centimeters. Let's have a look on some tricks. Regarding the polarity, okay, we said the connector must not heat over 30 Kelvin, but only with a 3-pole connector. What is happening when we use the same connector in 12 poles? What do you expect? Our expectation was this one. So the temperature will go up. but reality is a little bit different. This has to do with the security margin we have on our connectors. We always have a security margin around 20%. And we have now more plastic material, which is good for radiation. So here the radiation is smaller because the connector is smaller. Here the radiation is bigger because the connector is bigger. So that means we can use the working current you can read in our data sheet for all polarities of our connectors. We do not have to respect polarity in this case. It works for all connectors thanks to the security margin and thanks to the radiation dissipation. What is about when we put a connector in a closed box? We just made a test with a closed box too. And here you can see the box internal temperature in blue and the connector temperature in brown with outside connector and the closed box. And you see the connector temperature is much higher and also the box internal temperature is higher. But there's another thing which is more bad, which is worse. The time for the stabilization takes long and very long. So what can we do against this? We tried it with some holes in the box. Thermal energy is stored in the box, not enough exchanges. Convection does not work in a proper way. So this is why we put some holes in the box and tried it with the holes in the box. It gets a little bit better, as you can see on the connector temperature here. Also the box internal temperature goes a little bit down and the time is much lower for stabilization. So this is a little bit better than without any holes in the box. But we have still the wires inside. Holes at the convection decrease, okay, stabilization time and temperature. What when we close our box and put the wire outside with external wires? Then it looks also better. Then the connector temperature goes down again and the box internal temperature too. And what about the stabilization time? It's just the same thing. It also goes down. So it is a better idea, yeah, to have external wires than holes in the box, for example. They add the conduction effect. We have a better effect than the holes. So now we do something else. We use 15 amps instead of 20 amps, or you can also use a connector which is suitable for higher currents. On the other side, it's the same thing. Then the time for stabilization goes down very fast, and the connector is not warmer than outside of the box. So that means the best thing to reduce the heat if you have a closed box is to take the biggest connector which is possible and the biggest cable section which is possible and put the wires outside. Then you are on the best way for your application. Because of the I-square rule we saw before. So what to remind? Use working current for all pole numbers in a closed box, put maximum of the cables outside, oversize the cables if possible and the connectors. Yeah, should I decrease current after several mating cycles is also a question which customers ask us often. So therefore we made also a test, but we are really conservative regarding our mating cycles. Here is a mini module connector from our portfolio and we tested it. The data sheet says 25 mating cycles and we increased the mating cycles up to 200 and as you can see not many things happen here. So the resistance does not rise in a fast way, or so it doesn't. You can respect the mating cycles in the data sheet, and if you do not go over the mating cycles, the contact resistance will never increase. That's what we guarantee from the wood electronic side. Then we have some deep terminal blocks. They have a screw system inside. So some people say, oh, isn't it good to add a higher torque on this screw? Is the delta T proportional to the tightening torque? We also tested this, and at the end, it is not. So this is a rising cage system, as we have it in a lot of terminal blocks. You can see it here. And we have a data sheet torque, which is in the data sheet mentioned, of 0.4 Newton meters. And if we go higher than 0.4 Newton meters, we just get mechanical stress on the components here, but we do not increase the resistance anymore, or we do not get a better resistance, let's say it like this. If you respect the tightening torque in the data sheet, you're on the best way, and the connector is safe regarding the mechanical stress. Do not overscrew, do not take higher torques as given in the data sheet. So the last point is the derating curve. And there are two derating curves, one for UL and one for VDE. I think the UL is the more interesting for you today. So how can I decrease the current when ambient temperature increases? We have to respect the maximum connector temperature, and we have to respect the 30 Kelvin, and we have to respect the I-square rule. So I give you an example of this connector here, a wire-to-board connector with 396 millimeter pitch. It has an operating temperature from -40 up to 105 degrees. And we have the current rating around 7 amps. Now, when we have a look at the UL derating curves, it looks like that. And we have to respect the maximum working temperature. It's 105 degrees. So that means the black curve is responsible for this connector. Now I want to know how many current can I apply to this connector at 90 degrees Celsius. So if we want to check this, we have to have a look here. And this is 70% in this case. And if we have 70% of the 7 amps, it's 4.9 amps we can apply at 90 degrees Celsius regarding the UL standard. Regarding the VDE standard, it's a little bit different, I told you before. And therefore, we have our terminal block again here. He has an operating temperature up to 120 degrees. It's another plastic material in this case. And VDE says we can apply 24 amps on this connector. And now I have the same question. When I have 90 degrees on my connector, how many amps can I apply on this connector? And in this case, we are allowed to apply 88%, means 21.1 amp on this connector at 90 degrees Celsius. But be careful with this curve. It's only valid for Europe. It's only valid for European applications. For American applications, we have to respect the US standard. So what do we have to remind? The number of mating cycles we have to respect in the data sheet has no influence on our delta T. Screw hardly TBL above tightening torque has no effect on delta T. It just gives mechanical stress on the product. Decrease current with the derating curves when you are close to the maximum operating temperature is the best thing you can do, respecting the derating curves from UL, as you can see here. And you can find this derating curve also on our website. Sometimes we have some design guides for connectors, and there is also the UL derating curve always mentioned and shown. So at the end, I wanted to show you some crazy things when we apply 3 times higher amps on the connector than allowed. So this connector, it's an MPC4. It's suitable for 9 amps at 105 degrees. We tried it out with 35 amps. And as you can see, it gets very, very hot, too hot for the connector. For sure, it gets 258 degrees Celsius, but it didn't burn. So it's a horror current, it's a working current multiplied by 3, but we have no fire on our connectors. So this is because of the security margin we have in our plastic materials. Another example is the MPC3. It's suitable for 5 amps. We tried it with a 16 amps. We got also a very hot temperature, 248.6 degrees Celsius. It melted a little bit, the plastic material, but it also did not burn because of the security margin, no fire. So what do we have to remind finally? Working current is designed regarding UL standard with 30 Kelvin and VDE standard with 45 Kelvin. We have to respect the I-square rule. We see the formula here on the right side. Use derating current when you are close to maximum temperature. Regarding the thermal dissipation, undercurrent temperature should be stabilized after 10 to 5 minutes. So that means a closed box is not a good idea to stabilize the temperature. Use the working current for all pole numbers. It's possible. The wire heat less than the connector, and the wires can be used in a perfect way to dissipate the heat, to suck it out of the connector, and the optimized length for that is between 10 and 15 centimeters. If you have a closed box, please put your wires outside if possible and oversize the wires. And we have a big security margin. This is huge for our connectors. Plastic is just melting, but it's not burning. So if you respect those things, this will never happen. Create a thermal exchange with outside, and you will never see a picture like this in your application. So I hope you could enjoy my small presentation. You could enjoy it. And now it's time for your questions, and I will give you some answers if it's possible. And if I cannot give you the answer directly, I will take the question with me and I will send you an email afterwards. Thank you very much for listening. So I would hand over to Amelia again at this point.
Wonderful, and thank you so much for presenting today. We did have some questions come in. Not sure if you are able to see them at the moment. We do have one of the questions here asking about PCB tracks. Can I optimize these two in my application?
Yes, it's possible to optimize the PCB tracks in the application, but the PCB tracks have not that big influence on the whole system than the dissipation through the cable. That's why we told you about the dissipation in the cable first, and we did the tests with the PCB at the moment. So, but I can give you a very good information at I think in July or August when we are ready in our labs with our tests, and then I can tell you how to optimize the tracks too, and you will find this also in the design guide for our terminal blocks. Then online, let's say about in August, it has to be online on our web page. Okay, I see another question here on the ULD rating slide. Why is the connector rated for 105 degrees Celsius? And this is quite easy. Remember the relative thermal index for our polyamide. This connector is made out of polyamide. It's a PA66 made connector, and therefore we have a relative thermal index of 125 degrees Celsius. Remember our security margin. This is the reason why we rate our connector for 105 degrees Celsius. Then we are always on the safe side. Even if this connector is running for a long time, for 10 years and more, the plastic cannot accelerate faster than it should because we respect the relative thermal index. That's why the connector is rated for 105 degrees.
So we have another question here. Regarding the derating curves, are they only for power connectors or are they for every connector?
Okay, let's say like this, for the power connectors, you can find the derating curves always in the data sheet. There may be some connector without a curve in the sheet, but we are just adding this. So we started to do derating curves with our power connectors because there it is very important to have a derating curve, but we are also come step by step going to the signal connectors. But this temperature rise test, as you can imagine, takes a long time. So for example, if we want to test one connector in a proper way, it takes a whole day for us, because the temperature has to be stabilized 15 minutes, and then we have to do the measurement again, and so on and so on. Then the next temperature step, then it also has to be stabilized for 15 minutes, and this takes a long time. So this is the reason why we do not have for every small connector now derating curves available, but we will create them more and more because it's more and more popular to use a derate to get also some small currents over the signal connectors, and then we will also offer a derating curve for every connector in the future. So are there some more questions?
Yes, it looks like we do have one here. In an application using a surface mount fuse holder where the current is very close to the fuse holding current, what are the best practices for layout and enclosure to minimize the temperature rise and life derating?
Yes, in this case, you also have to take care for the cable. Please use the biggest square section of the cable which is possible, and then you can use your fuse regarding the hottest temperature which is suitable for the fuse holder and the fuse, and the cable will dissipate the heat out of your system. So here it is important to use a big square size of the cable and to put the cable a little bit away from the connector itself, or from the fuse holder in this case.
Okay, and we have our final question here. If your question doesn't get answered, then we will answer it after the presentation. This
Sure.
one goes out to our northern neighbors. They want to sell the application to Canada. What standards do they have to use?
Yes, they have to use the CSA standard, or also the UL give standard. It's called CUL-US. And if you look on our data sheets, you will find either UL sign or CUL-US sign. If you can read the CUL-US sign, this product is already specified for the Canadian market. So the UL certification organization also specifies for the Canadian market, but then it's called CUL-US.
Okay, thank you very much, Stefan, for presenting today. We really appreciate it.
You're welcome.
And thank you for joining us for today's Worth Electronic webinar. Now, as a reminder, if you have any questions or if we didn't get to them, if you think of them later, simply reply to our follow-up email at hereforyou@we-online.com, and we will make sure that you are all taken care of. Don't forget to register for our next webinar later this week on the 6th. It's LAN on Command. We're going to learn about the importance and the selection of LAN transformers in Ethernet devices. And if you want to stay up to date on our webinars, you can always follow me on LinkedIn and follow our corporate pages, Worth Electronics. My name is Amelia Thompson. Thank you for joining us. And again, may the 4th be with you.
Thank you so much. Bye-bye.